Okay, so we are getting back to the business of pitches. So into our second round. Next up, we've got Monolithium.
In 1979, lithium-ion battery technology, which you find in your smartphone, Tesla, and laptop computer, was invented in the lab of Dr. John Goodenough, a former US military scientist during World War II and longtime MIT Lincoln Lab researcher. 11 years later, the first lithium-ion batteries reached market in Japan, commercialized by Sony and Asahi Kasei. No, not by an American company. Today, lithium-ion batteries enable us to drive electric vehicles, reducing air pollution and greenhouse gas emissions. We know what the cost is if we don't electrify: more severe weather and destabilized society. But lithium-ion batteries are riddled with problems. The fundamental technology hasn't changed in the last 40 years, and lithium-ion batteries contain toxic flammable components that can cause damage and loss of life. Notice the dates on these headlines: August 2021. This is a real, ongoing, current problem. General Motors is reaching back to battery maker LG for financial responsibility, and the problem is so serious that GM has advised owners not to park in their garage or near buildings. Lithium-ion batteries require special cooling and battery management systems to ensure they don't overheat and catch fire. Inevitably, some do. There's also another dirty side to lithium-ion. They use child labor to mine for an essential ingredient, cobalt metal. We offer a fundamentally different battery. No other battery company today is doing what we're doing. We are cobalt-free and completely solid state. No toxic flammable solvents, no battery management systems, no cooling systems, no forced child labor, and we do it cheaper, all while providing fast charge under 10 minutes and high voltage, and the possibility for a reliable American-owned battery supply chain to protect our national security. Today, the vast majority of batteries are manufactured in China. We are here to strengthen the American battery market and provide unique applications for the $200 million defense market, as highlighted as a national security priority by the Department of Defense and Department of Energy. Our technology provides savings in weight, size, and allows us to go to higher temperatures without risk of explosions, while offering higher voltage and fast charging. Our dual-use technology is suitable for power tools, wearable health monitors, electric vehicles, tactical microgrid storage, and unmanned aerial vehicles. You can take monolithium in your checked luggage, and we make air shipping easier for defense supply chains. We conducted extensive customer interviews with leading companies and DoD customers to find their pain points. Monolithium hits them all with low cost, solid state, fast charge, and high temperature operation. Monolithium is a fundamentally safe battery due to the unique microstructure of the battery developed by scientists at the Army Research Lab. The battery market today is worth $39 billion and expected to reach $116 billion in the next 10 years with a 12% CAGR. We're looking to meet the needs of the $800 million serviceable obtainable market and $200 million DoD market. Every company today is trying to make a better battery using the same old lithium-ion technology and solid electrolytes or barrier coatings. We're pushing the field into something completely different with our monolithic technology. Instead of multiple barriers and coatings, we offer a gradient battery where electrons and ions can flow due to the unique battery microstructure. Our team is incredibly talented and experienced in bringing technology products to market. I researched new battery materials funded by the National Science Foundation and Mitsubishi Chemical during my PhD, conducted new energy research as a Fulbright Fellow, and founded and ran a digital health startup. My co-founder, Dr. Jack Salerno, also has a PhD in material science and has founded and led multiple companies and is an inventor on over 30 patents. Our other co-founder, Brian Canaday, is a former U.S. Air Force colonel and was the first Chief Innovation Officer of the Air Force and stood up multiple innovation hubs for the Department of Defense. We understand battery chemistry and we understand the customer's needs. Our technology is patent pending, and a prototype was made this summer. We expect manufacturing process development through the end of next year and a commercial product in early 2024. We're seeking smart money and strategic partners and have a $200K ask to get us through the manufacturing process development as we apply for non-dilutive money. We will use the $200K to get us to the next milestone. Imagine if you had invested in Nobel Prize winner John Goodenough's lab spin-out. We'd like to see this technology stay in the US. Choose Monolithium, the safe battery for the 21st century. Thank you.
Okay, we are back at it again with another battery-related technology. So, Monolithium team, welcome.
Thank you.
All right, are you ready to jump on the hot seat and answer some questions?
Yes, we are.
Okay, well, I think we have plenty, so I'm going to start with Tex and then move on to Brian.
Yeah, thank you. Really interesting, and I'm very intrigued. I would like to understand more about how it actually works. I couldn't tell from the pitch exactly what it is, other than that there's some microstructure gradient, but I don't know how this battery actually works compared to current lithium-ion batteries, nor is it clear to me how you manufacture it. Can you comment a little or explain a little bit more about both of those?
Sure. So without getting into too much detail to protect our IP, the battery is all solid state. So it's the same as a lithium ion battery, except each component is solid state material.
And from a manufacturing process standpoint, does this require all new manufacturing equipment? Is this something that you would manufacture yourselves based on the new equipment, or is this a technology you would license to current battery manufacturers?
So this is a material that's suitable for current manufacturing processes, but has the potential to be manufactured in a simpler way than some of the techniques right now that rely on solvents, because we are solvent free, so there's no liquids.
Okay.
If I can expand on that, this is sort of a ceramic battery structure. It's a little different. It's an all oxide, and so it can be made and manufactured with conventional ceramic processing techniques, meaning industrial ceramics, not pottery.
Right. Thank you.
All right, great question, Tex. Brian.
Yeah, fantastic presentation. So right now, what are you guys projecting for your kind of watt hours per kilogram for your energy density on this technology?
So it's comparable to current lithium ion battery energy density, but we do need to do further testing to see how we can put together the materials in series to get to high energy densities.
Okay, so like low 200s, is that fair, or high 100s? Yes. Okay. And then, so your power density, what is that looking like? Does that have current limitations on your output, or are you pretty much same as lithium?
So we are higher voltage than lithium. Okay. I think it's in the ballpark of 3.5, 4.
And perhaps to go back to address the other question, just another thought. There is no metal lithium involved. There is no actual lithium, metal lithium component. Of course, it incorporates lithium, but there is no metal lithium layer in our battery, which makes manufacturing much more simple because, as we all know, lithium is rather unstable in air.
And then the last question, have you guys looked at getting some of those certifications at like Carter Rock and some of those other facilities to allow this to go on like submarines and aircraft and places that you can't put lithium ion now?
Yeah.
That's part of our plan.
In fact, we've talked directly with the people at Cataract that do these certifications, and they're quite interested in this and actually pointed us in the direction of submarines.
Okay. Yeah, I had one more. Sorry, I kind of lied. So there's other groups doing 3D printed batteries like Carousel and Saku. I don't know if you're familiar with those companies. How are you guys different? What's your differentiator between those 3D printed battery technologies?
So I'm not familiar with those companies, but there's potential for us to do 3D printing with ours as well. So I'm assuming it's just the materials that they're using is a different set than ours.
All right, thank you. Very good.
And I would say that I don't think that people have yet solved kind of the uniqueness of the interface challenges. And so I know that's one of the uniquenesses to our approach for 3D printing, so that we'll be able to do it more from a single structure versus a single phase.
All right, thank you, Brian. Jessica.
Hey, thanks everyone. I had a question about, do you envision this being something that can be a replacement? So would you offer a product where you can actually replace current things that are using lithium batteries versus would this only be for new products that are being created?
So we imagine supplanting the current lithium-ion technology space, as well as being able to use the batteries in areas that you can't currently have them. So, for example, shipping them via air cargo, putting in your luggage, having them in submarines and airplanes.
Okay, and I know that there's like a wide market that you're looking at. Do you have a specific go-to-market strategy in terms of who you're targeting first?
Yeah, we're looking at the power tool market, as well as the specific DoD applications I just mentioned.
Okay, great, thank you.
Thanks.
Okay, time for a final question. Any other judges? Okay. All right, so Monolithium, you are officially off the hot seat. Great job.
Thank you.
Thanks.
Hi, my name is Dominic Doctor, and I'm from Protocom Technologies, where we're the future of RF design. Let's go ahead and right into the problem. So as you can see on this left-hand side, this picture kind of shows you the struggles of RF system innovation. And so for one thing, all the components have different specifications, and your RF engineers have to worry about compatibility issues. And that's because there's an inherent lack of standardization across the industry. And also look at those wires. It's very messy and consistent, confusing to see what's going on. And so if you need to troubleshoot, well, your development cycle is now being prolonged. And it's clamped down to the table. So you can't really take this out of the laboratory setting and put in a vehicle to validate your design in field. So it's very inconvenient. But once you do validate your design, you're off to the manufacturing phase. But I wouldn't be too excited because that opens a whole new set of problems. What happens if this breaks, or if this chip fries, or if this doesn't meet dimensional specifications? Well, there's a new design iteration in store for you, which leads to long lead times, especially now with the global chip shortage. It's also a closed system and it's not modular. And so there's no resource sharing and you can't really swap in things out if something goes bad. And so you're vendor locked because now if you have a repair that's needed for this heavily integrated electronics, well, you have to send it back to your big prime for repairs. And so here's the solution. We're going to use an example from the US Army. What they wanted to do is they wanted to come up with the C4ISR EW Modular Open Suite of Standards, also known as CMOS, and this would address the following problem. On the left-hand side, you see this vehicle, and this vehicle is overburdened by 10 to 15 communication platforms, and they all have this parasitic effect. It's just too overburdening. And so what they want to do is they want to come up with an agile solution to replace it by a CMOS chassis with these different types of profile cards, roughly the size around a hard drive. And so all of these different profile cards, they would have the functionalities of these different individual systems. However, they're all integrated into this united, interconnected system. And so this eliminates the competition for resources, excessive heat generation, redundancy in the subsystems, and avoids high costly maintenance fees. And so this leads into a new global defense strategy known as the Modular Open Systems Approach, MOSA for short. And so at Protocom Technologies, we like to consider ourselves as a smart grid for your RF systems because we're exactly doing that, but we're taking it a step further. Take a look at these drop-ins on the right-hand sides. These are all commercially available. They're standardized RF components, and you could easily interconnect them with the little bridge. And so our solution is on the left-hand side, where we have a metallic plate that we can easily innovate a design by just taking these components, screwing them down, and then sending individual power signals, control signals, and communication signals with this printed circuit board to all these components. And so now think about this. Here's an example design. And so this is an RF front-end transmitter architecture. And so you have this schematic with all these different standardized components. You just have to plop them down on this metallic plate and screw them down and interconnect them with that little bridge. And then you could put it in field to test autonomous cars for 5G applications, for example. And so there are endless possibilities. We currently stand at a TRL between 5 and 6, depending on the use case. And we come in 3 different configurations, 3U, 6U, and even space VPX standards. For our modular feature, we can easily swap in those standardized components if something goes wrong. And so we can really innovate the design. And so thereby we reduce the cost because now different companies can actively compete for those different components being application specific. Also, we're low swap, so we save size, weight, and power. We're ruggedized for harsh environments. We're also system interoperable. And so this is an open system, so you can easily interconnect those solutions to scale into large complex solutions. And you can easily take this from the lab and put it on a vehicle or inside those CMOS chassis that we saw earlier, and we have in-field viability. To close certain technological gaps, we want to quantify testing and evaluation. And so that includes stress, strain, temperature, RF performance, make sure we're MOSA compliant, so that would be the MORA and Victory standard, and design simple architectures such as the transmitter, receiver, and transceiver. Let's get into the market. So here's the C4ISR market analysis. For the total available market for C4ISR, by 2022, we believe that that's going to be around 142 billion. The serviceable available market of communications around 50 billion by 2022. And we believe that Protocom Technologies can obtain around 0.9% of that serviceable available market by 2024, which estimates around to be $480 million with the CAGR of 3.5%. Looking at the competitive landscape, we believe that our company across all these different comparisons amongst these primes checks all the boxes for modularity, field operability, 6U and 3U VPX standards, standalone standards, which can be bolted on any surface, RF communication and microwave communication domains, and we can drastically cut down development and prototyping time. We've also discovered different civilian markets, such as law enforcement and first responders. For law enforcement, they've discovered that the fleet costs around $50,000 for the vehicles, and to retrofit them, it's around $70,000. We believe that our technology can reduce the costs, thereby increasing the fleet size. Also, if the communications are down, your car's out of service for around 2 to 3 weeks. That's a long time. And so we believe that with our device, we can easily repair the product on site. For the Internet of Things market, there comes an issue where we have to replace the entire systems for communications to increase bandwidth. And so we meet that operational flexibility by meeting long-term needs using our system. Additionally, those functionalities are limited because there's no sharing of resources. They're all closed systems. And so, again, our technology enables the sharing of those components. Our company is as follows. I'm Dominic Doctor. I'm the CTO. I head R&D and product engineering. Giovanna Patterson is the business administrator. She heads the grant and contract writing. Jason Rutledge is our CEO, and he's our system integrations and solutions expert. Our mentor at FedTech was Michael Okren, our entrepreneurial guru. Tony Marash was our coach at FedTech, and he is a defense strategy and emerging technology expert. We believe that we also have a little technological gap in our skill sets, and that would be the RF engineer for vice president of engineering. Here's our product roadmap. By Q3 of 2021, we would like to end FedTech's phase 2 program, commercially evaluate our technology. We've already incorporated our company in Texas, and we've applied for 2 prize competitions. By Q4 of 2021, we want to initiate the contracting phase, and that's to create our minimal viable product, apply for SBIR, STTRs, initiate CRADAs, and do some talent scouting. For manufacturing, we want to start that by Q1 of 2022, and that would include manufacturing agreements and expand product configurations. By Q2 of 2022, we'd like to enter the development cycle, where we lead research and development efforts, optimize the product, do RF component partnerships, and debut our flagship product. For funding and collaboration initiatives, we've done the following. For competitions, we are participating in XTech Plug Fest and XTech Search 6, both of which have a first schedule prize of $5,000 each. We're also looking to SBIRs for this upcoming fiscal trimester, and also want to initiate CRADAs and look for grants and investors. We believe our first potential customers might be the US Army and the Texas Department of Public Safety. I'd like to thank you for your time, and I'll leave you with this ask. We're looking for future investors. We also want to have connections with the IoT industry, and we're seeking connections with RF engineers for talent scouting purposes. And we're also looking for domestic printed circuit board manufacturers. And if you have any questions, please feel free to contact us at info@protocom.tech or look at our website at protocom.tech. Thank you.
All right, Team Protocom, welcome.
Hi, thank you, Mike.
Hey, great pitch. And are you ready to get on the hot seat and answer some questions?
Yes.
You bet.
We are indeed.
All right, I see Brian is primed and ready to go. So Brian, kick us off.
Sure. Dominic, first of all, my condolences to you Aggies and losing your starting quarterback last weekend. All right, I want to make sure I had this straight, from your presentation. I'm actually formerly an RF design engineer that used to work in Greenville, Texas. So I know your area well. So you're basically creating a circuit board kind of backbone upon which you can bolt down RF modules that are just out commercially in the field, and then you're going to kind of bridge them together. Is that correct?
That's exactly that's exactly it. That printed circuit board is actually the proprietary part of that entire module, where we're able to interconnect those plug and play style little onboard modules and send power control signals and communication signals as well. And then we're able to also adapt that with certain VPX standard, open VPX standard interfaces.
Okay, so talk to me about your bridge concept, because there are things like phase matching and visual and impedance that you've got to all get right between the modules. So how do you envision that bridge? You just kind of mention it, but can you give me a visual picture of what those bridges would look like?
Right. So there is a interconnecting bridge that is commercially available. And if you can imagine it, you would piece all of these different types of commercially available modules, like a phased lock loop or an amplifier. And this bridge is a metallic piece that goes from one end of one module and connects it to another one, and to ensure some RF stability in between those. I believe everything is accounted for in terms of impedance matching. There is one specific company that provides a variety of these commercially available units, and so everything is accounted in that sense.
What about the phase? How would I, say at 8 gigahertz, make that bridge be the phase I need it to be for the next component?
That's the design, that's the engineering that would go into each of the components. You pick the right component that does the job that you want it to, and then the programming part of the board is what allows you to send whatever specific power frequency signals, whatever you need, to each of those individual drop-ins, sir.
Right, but if I need the phase to be, say, 9 degrees between two components, like say for a hybrid, how would I make that 90 degrees at, say, a certain frequency?
Right, so
that would be the RF engineer that we do not have on our staff, sir.
You're throwing it on the RF guy. Yeah, I know. I get a lot of that stuff. All right. No, I don't want to bust you up too much, but yeah, those are things. I mean, I think you guys are onto something. I think you got some really cool ideas and technology. I think there's a couple of things. The bridge is going to be probably more challenging than just putting a, it's not like basic electric circuits, right? Where I just put a wire across two. Yeah, there's going to be a little more to it than that. And maybe you'll have to do some custom bridges, right?
Sir.
Yeah, go ahead.
Sir, if I may interject, so I come from an optics and photonics background, and from my understanding, what you would do is you would have to delay one branch of, let's say, if in a spectroscopy setting, to have some sort of phase delay. And so I would assume that there's some sort of block there that induces a phase delay of either 90 degrees or 180 degrees. But that would require a little bit more background research in order for me to get a complete understanding of the different variety of components available to us.
Yep, you're correct. You got the concept. So yeah, like I said, you guys are onto something. I think the bridge needs a little work, but fantastic presentation, and very interested to follow you guys and where you're going. So
thank you, sir.
Thank you.
Oh, great job. That was some tough questions, Brian. All right, opening it up to the judging panel. Chris, let's see, you came off of mute.
Yes, so in looking at your competitive analysis, it looks like, in the standalone category, you kind of view yourselves as being set aside from the rest of your competitors. I noticed that wasn't checked off anywhere else. Is that a particular barrier to entry or something that you believe really sets you apart and will keep you standing apart, or how do you view that as a competitive advantage in particular?
Right, so in particular in the standalone configuration, with the other competitors that we've looked at, such as the big primes listed on that landscape, from my understanding, they have specific modules accustomed to 3U VPX, 6U VPX standards. What the standalone configuration is, it allows you to bolt it down on a specific surface and then interconnect it with a microcontroller without the need of a VPX chassis. And so from my understanding, from the research that we've done, I haven't seen that specific capability from the big primes that were listed there.
Is that something that would be difficult for them to replicate and to take away a competitive advantage you may have, or is the ability for you to do that really proprietary to your particular product?
I would say that it is slightly proprietary due to the specific interfaces between that microcontroller and that blue printed circuit board that the patent has been applied for.
Thank you, Dominic.
Hey, judges, any additional questions? All right. Protocom, you've got them stumped, except for Brian.
We'll take that as a good thing.
Right.
All right. Well, hey, I think you've got some follow-up with Brian to do for sure, but Protocom, great job in the program, great job here pitching, great job answering questions. I really enjoyed working with you all.
Thank you.
Thank you,
Well,
ladies.
thank
We
you.
as well. Thank you.
Have a great day.
All right. So moving on to our final pitch, we've got Team Elvy.
Hello, I am Sarah Myers, part of Team Elvy. Elvy provides performance vision for your lower legs. Soldiers' musculoskeletal injuries cost the Army more than 8 million duty days a year, at an estimated cost of $19.2 billion. Musculoskeletal injuries far outpace any other reasons for lost duty. Among new recruits, 45% are injured in basic combat training. Lower extremity overuse injuries account for over half of the injuries during basic training. There is a need for detailed information on the forces acting on soldiers' musculoskeletal systems, as well as how their movement is affected by the terrain, loads they carry, and other obstacles in their navigation environment. Elvy is a smart fitness wearable. Elvy consists of instrumented load sensing insoles with ankle packages, providing bilateral lower limb movement information that can alert soldiers to potential injury risk. Elvy can be inserted into footwear of all forms, including running shoes and combat boots. This allows Elvy to be paired with your favorite or required footwear. The insights provided by Elvy measure lower leg performance and can reduce the risk of injuries. Our conversations with the U.S. Army Combat Capabilities Development Command revealed to us that current approaches for measuring gait in the field face issues related to portability, connectivity, and durability. Ease of application, consistent placement of sensors, and time to instrument soldiers is also a challenge. Elvy is an easy-to-use, markerless kinematic and kinetic capability, and with its 16+ hours of battery life, Elvy can acquire lower leg biomechanics data all day long. Elvy is even sensitive enough to detect when the wearer is about to get a blister, before the blister has even formed. Here is an example of Elvy being able to detect differences in mobility and agility between a no-load and a loaded condition. In pilot studies with soldiers, Elvy detected changes in lower leg movement characteristics in real time. All of this data allows Elvy to predict overuse stress injuries before they occur or detect the occurrence of an acute injury before it becomes severe. This is the mission of the U.S. Army Combat Capabilities Development Command Soldier Center. To achieve this mission, training regimes and physical fitness tests need to be modernized. Elvy is a biomechanical tool that can provide data to guide this modernization. Elvy aids in the design of boots, individual body armor, and load carriage gear to reduce injuries, delay fatigue, and enhance dismounted warfighter agility, mobility, and operationally relevant performance. Elvy meets the specific needs of the U.S. Army Combat Capabilities Development Command, but all service branches are trying to reduce injuries during basic training. If we are to treat the soldier as the DoD's most valuable asset, it is ideal to prevent injuries and promote effective physical training from the outset so soldiers can complete their missions. If successfully realized, Elvy can be used across the different branches and commands of the DoD. By using analytics to predict readiness, increasing performance with guided training, and supporting missions with real-time monitoring, Elvy quantifies soldiers' physical readiness. New equipment can also be qualified in terms of measurable outcomes on soldier performance. Or following injury, Elvy can monitor and aid in soldiers' recovery. No existing competitor meets the environmental needs of the DoD, hence the Army is actively funding research and development to fill this gap. Commercially available consumer smart insoles do not meet the accuracy requirements, and research-grade insoles are fragile and cumbersome to use. In addition, existing systems are limited in their battery life and force sensing capacities, important considerations given the length of missions and heavy loads carried by soldiers. Elvy is powered by mobile, developed and patented by MIT Lincoln Labs. The second-generation prototype is being built for a narrow use case, and we expect it to be completed this fall. Following successful feasibility testing, broader Army field trials will be completed in early 2022. Elvy will perform new research and development SBIRs to optimize data analytics for Army areas of interest, including fatigue, gait biomechanics, agility, and soldier load metrics from field and obstacle course testing, as well as testing the performance impact of potential new equipment. Phase 2 will focus on tailoring Elvy based on the analytics outcomes, design for manufacturability, and data transfer to appropriate stakeholders. Upon success, we will begin approval for DoD procurement and engage with other DoD end users, which might include special forces, medical recovery, and Army research laboratories. To bring Elvy to market through co-development with the DoD is a clear path forward. Elvy has an engaged Army stakeholder with identified end users. We plan to leverage those relationships to further develop and validate the product. There are over 2.5 million service members in the DoD, and each year the DoD seeks 150,000 new recruits, all of whom must complete basic training. We've conservatively estimated that 10% of new recruits might use Elvy at any given time, which would result in 15,000 units per year and an annual revenue of tens of millions of dollars. The R&D scaling process from Phase 2 to Phase 3 and beyond will allow the Elvy team to grow as needed while maintaining a clear vision for the future. As we move into SBIR Phase 2, we plan to add software developers and manufacturing capabilities. As the product nears production and manufacturing is scaled, we plan to expand into the competitive and recreational fitness markets and possibly medical markets. Both markets are valued at billions of dollars. Expanding into new markets will require the addition of expertise in the athletic performance and healthcare domains. Our founding team is adequately equipped to execute the plan. Bobby Azuda has completed numerous DoD SBIRs and rapid product development efforts. Sarah Myers is a biomechanics research expert, and Julie Yell is experienced in federal government contracting and located in Washington, D.C., near important stakeholders and Army proving grounds. Joe Lacronoa, the inventor of mobile, is a mechanical and biomedical engineer at MIT Lincoln Laboratory. Brian Cross is a marketing guru, investor, and advisor for sports and esports tech startups. Mark Condaus is a high-achieving executive with a track record of success in the healthcare landscape. We are actively seeking advisors to realize Elvy's fullest potential. If you want to follow up with our team, you can reach us via email or through our website.
All right, Team Elvy, great job. Are you all ready to answer some questions?
Yes, we are, Mark.
Yes, we are.
I'll take Mark, that's fine. All right, so hey, let's go ahead and get you teed up. We've got a lot of judges with hands up. So let's start out with Dash. I'll move on to Jessica and then Brian.
Thank you. That's a great presentation, Sarah. Just had a question is, this is something specific to mobility only, or can this be, I'm just thinking like a pilot perspective, is this something that can be worn by a pilot during operations, or does it require a person to keep moving to be have any analysis?
Yes, that's a great question. So depending on what you want to use it for, there doesn't need to be movement to actually collect data. So you can get information about position of different limbs or body segments from the IMUs, and also position information about the forces in different body segments from the sensor. So if you wanted to look at seating, for example, or load on a different part of the body, that would be a completely different device application using similar sensors.
Thank you.
Great question. Jessica.
Hi, I may have missed this during the presentation, but can you clarify how that data is being shared? Would this be through an app in real time that a user can look at, or how are we receiving that information?
Right, that's a great question. So right now the information is going through Bluetooth to a tablet or a smartphone device. And the data, a lot of data is being sent right now. So one of the goals of the SBIR development process is to determine what information is most important to display and to which users. And so we envision having a hybrid model where certain important information can be displayed real time, either to individuals or to commanders, and hopefully we can integrate that into their existing communication devices. And then we would also be able to download more detailed time series information later on.
Okay, and just as a follow-up to that, what would be the pricing structure for that? Are you charging for the product itself, and then would there be a subscription model for the data? Because I'm assuming your team would monitor the data, correct?
Right. So we envision for the Army, for example, which is our kind of initial target customer because they're a current sponsor and we're collaborating, we envision it would be selling a certain number of the devices and including in the contract a certain amount of support to them so they could use it and we could help with interpretation of the data and that kind of thing. And then in terms of the fitness wearables space, we have talked a lot about what would be useful as a subscription model. So in the fitness wearables space, which is kind of our secondary target market, we would have purchase for product with probably a certain baseline amount of information available with a subscription model.
Okay, thank you.
Thank you.
Great question. Brian.
Yeah, great presentation. I think you guys have another use case too. I think with your device, you'd be able to do injury detection, lower leg injury. Just, soldiers hate to say they're injured, but in training, you'd be able to see them favoring, one leg or the other, or taking pressure off of a part of their foot. And I guess you would have to hook into BatDoc to do that. But I think there's definitely some exploration there for a use case. Have you guys been working with the Gruntworks folks for the Marines? Are you familiar with that group out of Quantico?
We have not been working with that group right now. So our initial customer has been the U.S. Army Medical Material Development Command, and they're the initial sponsor of the device with MIT Lincoln Laboratories. We did quite a bit of customer discovery with different areas of the military, and we are learning that there's probably an infinite number of ways that this could be used and applied.
Yeah, I agree. They're definitely interested in that kind of human performance and human factors. So real quick, what is you guys' magic? Is it the pad, kind of the insole with the pressure, or is it the Bluetooth device, or what exactly sets you apart?
Thanks, Brian. Oh, you want me to go, Sarah?
No, yeah, I was going to pass it to you, Bobby.
Thank you. Yeah, thanks, Brian. There's a few different components of the system that make it unique and innovative. The first one definitely is the load cell sensor itself that's located within the insole. And so existing competitive technologies are using capacitive sensors, while the sensors developed at MIT Lincoln Labs utilizes strain gauges combined with a unique spring-loaded system to allow it to measure higher strains, forces, and loads, which increases its durability, sensitivity, and reduces its power requirements. Coupled with that, though, there are additional sensors such as different IMUs, a barometer that allow you to gain increased biomechanical data like ankle power, measuring whether soldiers are moving up incline or decline, and ultimately we have 44 different sources of data right now that we really want to refine down to usable data for interested stakeholders.
Okay, yeah, that's a lot more complex than I think you guys pitch it as. So is the IMU in that little box that's on the ankle?
Yes, there's IMU there as well as the IMU integrated into the insole as well.
Oh, wow. Yeah, that's impressive. So thank you guys.
Yeah.
All right, thanks, Brian. Trent.
Yes, I just wondered, to what extent is your very first customer, it sounds like Army, in terms of like, what are their requirements as far as durability and ruggedness, say, compared to who you think the next customer, I mean, let alone the consumer, is? I mean, it sounds like you guys are kind of front loading maybe really tough requirements up front.
Yeah, absolutely. So some of the requirements in the military are the durability that you mentioned, relatively long battery life, but others are just ease of use because soldiers already have so much equipment and heavy equipment. And so we want something simple that is just going to integrate into either running shoes or combat boots and is simple to put on. And then also being able to get that information quickly to the necessary personnel. So those are some pretty
Do we get a freeze?
I think we might have lost Sarah. She's on hotel Wi-Fi right now.
All right, Bobby, you're gonna have to clean it up.
Yeah, I mean, Trent, did that mostly answer your question? You have anything kind of follow-up you'd like me to answer?
Yeah, I think the question was really centered around actually kind of maybe even like the business model or the effort that you guys are going through. I mean, the product is impressive. I'm just wondering to what extent has your approach been to front load the more challenging requirements versus kind of incremental approach. I was just curious to kind of hear the thinking of the team on that.
Yeah, I mean, I think the biggest strength to our technology right now is we do have an engaged end user with an active ongoing contract. So like you said, the bar is set high, but we think we might as well leverage those relationships to really develop the technology as far as we can. Because then, right, the fitness use case, there's much less demand, there's much less loads. People may only be using it for while they're working out, less battery life. So we can really reduce it down to a much simpler device. So while we have that engaged customer, we really want to leverage that relationship.
Thank you.
You're welcome.
All right, Team Elvy, you did a great job. You are officially off the hot seat, and you are our last pitch as well. So thank you, Team Elvy, Protocom, Monolithium. Great second round there. And before we move forward, I'd like to take this time to recognize the judges. So on behalf of NSIN, FedTech, and the DIA program, you could have been anywhere else, but you were with us today. So really appreciative of that, and great feedback for these teams that went through this program. And I fully expect them to be reaching out to you here pretty soon as well. So to the audience, that concludes our pitches, and we're going to take a break until 4:55 p.m. Eastern. We're going to huddle here quickly and figure out who our top two teams are. In the meantime, please take advantage of the networking functions on this hop-in platform. This graphic up, you can see there's a little networking button, but also there's the expos. Each team that participated in our program, a total of 20, have a expo booth where you can go in, you can watch their pitches and interact with the team via chat. And then some of the booths, you can actually come up live with the team. So please do explore the platform. A lot of great use cases out here. We could only get 6 in, but we have quite a few that did well. So, but again, I appreciate everyone, and we will see you at 4:55 Eastern.